Hello everyone, welcome to the pre-recorded lecture. In this lecture, we will talk about famous classification algorithm that is your support vector machine. And in this session, what we will be doing, we will discuss briefly what is support vector machine, and after that we will see what is margin and how we are going to maximize the margin. And there are two cases in SVM. One is linear SVM, that is for data set that are linearly separable, and other part is non-linear SVM, that is for data set that are not linear, that are not linearly separable. So what we will see what we can do if we have data that are not linearly separable. So this thing we will be cover in this session, in this pre-recorded video. So let us start with a discussion. What is support vector machine? So a classification that has received a considerable amount of attention back in 1992. A paper is published by Wapnick relating statistical learning theory. So SVM has a root from this paper only, and from that time, the this algorithm become very much popular, and till date it has been used exhaustively for classification purpose, and a counterpart is also developed for regression purpose, that is your support vector regression. We will be not talking about support vector regression in this lecture. We will only focus on the classification part. So what it actually do, it searches for an optimal hyperplane, that is the decision boundary to separate the sample of one class from the other class. So how it work we will see in a minute, but there are few more things that I want to highlight relating, it is related to the SVM, that SVM work quite well with high dimension data. So there is no dimension related problem in SVM. Also, if you see, you can read about SVM that SVM while training SVM, it takes a lot of time, but the accuracy is very high. It means the training time is extremely high, but result means that the accuracy on predicting over the new data set is very high, and any processing on the test data is very fast, and there is a very less chance of overfitting in SVM. So I just want to mention that less chance of overfitting. We will discuss this point, that why there is less chance of overfitting in SVM, because of maximizing the margin. So let us see what is decision boundary, what is hyperplane. So as you can see in this diagram, there are two classes. One class I have represented by a positive sign, another class I have just represented it in, let me remove the background. Yeah. So if you can see, there are two classes, one represented in with a positive mark, one represented with a negative mark. So now our task is to separate these classes with the hyperplane. Hyperplane, since we are in 2D domain, there is two dimension case. So the hyperplane is a straight line. And if you talk about hyperplane in the 3D dimension, it is a plane separating two classes. So uh, if I ask you to draw a line that can separate these two classes, then you can one can tell me that okay sir, you can draw a line here. Let me use some different ink. Okay, blue, green. So one will say that okay sir, this line is perfectly separating these two class. One will say me that no sir, I guess this line is perfectly separating this class. So one may also say that no, the line in the middle is separating these two lines perfectly. And some people also say that instead of that, you can see this line is also separating perfectly. This line is also separating the two classes without any misclassification. So what you have learned that in case of deciding a hyperplane to divide the two classes perfectly, so there are infinite number of possibilities. So as you can see that we have found that there can be infinite number of line that can separate, that can be drawn. So one may ask that one may ask two questions. The two questions are whether all these hyperplane are equivalent or same. If not, then which is the best one? So as we have seen that these datas are given to us, okay, and so we will say that these are the training data, and over the training data what we have done, we have identified a hyperplane that can separate these training data perfectly. So the error, the classification error that is relating that is present in the training data set is zero. Means the classification error associated with the training data is zero. Why? Because we are visualizing the thing and we are drawing a line that can separate them without any overlapping. So the classification error is zero, but the main task is to select a hyperplane that performs exceptionally well on the unseen data, that is your test data. So I have told you in the previous session of CNN or ANN that there are two types of data. One data that we use to train the model to find different weighting coefficient and bias in CNN, and we use that weighting coefficient and bias to predict for a newer data that is completely unseen. That data is not used for the training set. That is called test data. So we will select that hyperplane uh, which can classify the things without overlapping and perform good not only with the training data, also on the test data. So for a good classifier it must choose one of the infinite number of lines, means one among these infinite numbers of hyperplane that performs not only on the training data but also on the test data. So to select one hyperplane, that one perfect hyperplane out of this infinite hyperplane, what we can do, we can take two scenarios. So let me uh, show you this diagram. Let me zoom out a little bit so that it is clearly visible to you. Yeah. So we have considered two hyperplane. Means we have selected two hyperplane, H1 shown in black and H2 shown in green. So hyperplane is exactly in the middle of the decision boundaries. So you can see that the dotted black line represent the decision boundary for the hyperplane H1, and the dotted green line shows the decision boundary for the hyperplane H2. So, and what is the decision boundary is something that is touching to one of the training data set. Okay, here you can see that this decision boundary touches the red data set. Here means the positive class, and here the decision boundary touches the blue class, means one. And similarly with the green case, the dotted green line on the left touches the red part, and that part touches the blue part. So this data, that this blue data, let me highlight again. This blue data and this blue data, this positive data and this positive data are called support vectors. Means these are the data that are important to decide the hyperplane, and all other data don't take part in deciding the uh, hyperplane, but the data that take part in deciding the hyperplane is called support vector. So I guess the idea is clear. What is support vector, and what which hyperplane we are going to select. So if you can see that you can means you can clearly guess which hyperplane we are going to use, either H1 or H2. So the if you can see that the margin of the hyperplane, margin is something that distance between one decision boundary to the other. So in this case this is the margin, and in this case this is the margin. Higher the margin, lesser will be the classification error. So let me write it for you. Higher the margin, lesser will be the classification error. So based upon this thumb rule, what you will do, you will select hyperplane H1 because the margin is high. So there are less chances for a newer data set to get into trap of the overlapping region and get misclassified. So the classifier that contain the hyperplane with a small margin are more prone to model overfitting and tend to classify a weak confidence on the unseen data. So that is the point that I have discussed, that we always go with the hyperplane that have a maximum margin. So I guess it is clear to you now that what is margin. Margin is the distance between two decision boundary, and why we are interested in maximizing this margin, because we are interested in reducing the classification error on the testing data. For that we have to ensure that the margin should be high, so that it don't get overfitted. As in case of H2, we are actually doing overfitting, and because of this overfitting, if you produce an unseen data, then there are high chances that it get trapped into another class. Okay, so this is all for maximizing the your margin. So what we will do, now we will discuss the linear SVM, and after that I will discuss the non-linear SVM. So in both the cases, what will be our objective? Our objective will be to maximize this margin. So to compute the model parameters, with corresponding to the maximum boundary. Once we get the model parameter, then we can easily classify. We will see that mathematically that how a margin is defined in through mathematical equations, and how we are going to classify the things. So let us start the linear SVM discussion. That SVM which is used to classify data that are linearly separable is called linear SVM. And let me write it mathematically that suppose each sample is denoted by xi yi, and where xi is xi1 xi2 up to xim for m dimensional data, means for m dimensional space. For 2D space it will be x1 x2, and yi is just a class level that either it comes into positive class or negative class. So in this lecture throughout we are limiting ourselves for binary classification problem. Later on, what you can do, you can the things that I will teach you about for binary classification, you can just extend everything for higher multi-class classification. So this will be your homework that you will be doing after this session. So just go and read how we can means sorry, how we can apply as SVM for multi-class classification. Okay, now let us see how we can write the equation of the hyperplane in 2D. So for a 2D training sample, uh, for a 2D training sample with attributes A1 and A2 as x equal to x1 x2, where x1 and x2 are the values of the attributes A1 and A2 respectively for x. So if you are asked to write the equation for the hyperplane, any of the hyperplane, then that hyperplane is a straight line, and you just need to write the equation for the straight line, which is nothing but ax plus by plus c equal to 0. That is something that y equal to mx in a modified sense. So what here that w naught is the intercept, w1 and w2 are the slope. So these things you can compute through the model parameters. So hope you can write a equation for any straight line based upon selecting any random 2 points, putting the value of x, getting the value of y, and you can draw a straight line. That is simple that you have done in class 6 or 7. So based upon that, any point that lies above the hyperplane should satisfy this equation, and any point that lies below that hyperplane should satisfy this equation. So if you can write this equation, you have if I ask you to write this equation in a matrix form, then you can write it in this form, that uh, matrix w dot product with matrix x, that is a vector w dot product with vector x plus b equal to 0. This is what we will be using throughout this session, because it is in compact form. Oh, what is happening? Okay. So what is the target here? What is our aim? Our aim is to just to find w and b from the training data set. And once you get that equation, then it is very easy to classify the things, because you know that the equation for the hyperplane is w dot x plus b equal to 0, and the equation for the decision boundary is w dot x, means dot represent the dot product, plus b equal to 1. Here in general what we can take, we take k, means w dot x plus b equal to k for, but just for the sake of simplicity, here we have taken 1, so that the mathematical part can be a little bit easier and things get very easy to understand. So, and as I have already told that the point that touches the decision boundary are called support vector. That means that all other data set, if you see, these data have don't have any role. These data have don't have any role in deciding the your hyperplane or decision boundary. Only this data that is already been marked and this data. These two data define your hyperplane, and that's why it's called support vector. So once we get W and B from the training data, then we are done. We are just we will compute W dot X plus B, and whether we check whether it is positive or not. In case of positive, it belongs to this class. If the value is negative, then it will belong to this class. So this is as simple as that. So let us proceed further. So we have yeah, one more important point that I want to highlight, that in class 6 or 7, where does it, yeah. So when we are in 6 and 7, then we have undergone through these equations. Let me write it for you, that 4x plus 6y plus 4 equal to 0, and 2x plus 3y plus 2 equal to 0. These two equations represent the same line. So what we have done, we have just normalized the weighting coefficient and the your intercept by a same number, that is 2. Then we get this equation. If you plot this equation and this equation, then these two equations are represent geometrically exactly the same equation. So that is the point that I have mentioned here, that if we scale W and B by dividing a non-zero constant, then we get the same hyperplane. Means, although what we have, where we have started from, we have started from selecting one hyperplane from infinite number of hyperplane. So we have selected one hyperplane, and we have selected that hyperplane which provide us the maximum margin. Okay. Now, once we calculated the maximum margin, then we get to know that for means different scaled value of W and B. Means when I say scaled value of W and B, then it must be scaled with the same number. Both the parameters simultaneously get scaled by the same number. Then there can be infinite number of solutions using various scaling factor, and all of them geometrically represent the same hyperplane. So to avoid any confusion, once we get the value of W and B, just make it unique. Just don't change it, because if suppose you can get a particular value of W and B, so what you can do, you can also use a scaled version of W and B to simplify your computational part. But I will not suggest to do so. Just go, because we will see that we actually in solving this equation, we get a means a lot of feasible solution. But out of those feasible solution, we will select one solution that will going to maximize the thing. And upon selecting that particular value of W and B, just be consistent with the use. Don't get means don't get into this thing that we can get a scaled value. Means we can scale the things and we get the same equation or not. So let us proceed further and calculate the margin. From the last 20 minutes, so what we are doing, we are saying that maximizing the hyperplane, and as I have shown you in this diagram, that this part is your margin, and let me define this part as D. So what we are interested in, we are interested in maximizing the D part. So let us see it from a mathematical point of view, that how we are going to compute the thing. So to calculate that D, what means, just focus on this part. Means it is very important thing how we are going to calculate the D. So let us suppose that there are x1 and x2 are 2 point on the two decision boundaries, and if these point are on the decision boundaries, then these two are support vector. So what we are assuming, that x1, let us suppose that x1 and x2 are two support vectors. Okay, so for these two support vector, it will satisfy the equation of the hyperplane on the left and that hyperplane on the right. And if we put if you can eliminate B by subtracting this equation, then you will get that the dot product of vector W with dot product of the subtracting vector, that is x1 minus x2, is 2. Just keep this value, and let us come to this diagram. So what we have done, we have assumed equation x1, a point x1 on hyperplane, and x2 on another sorry, decision boundary. Okay, let me do one thing. We have missed to draw the hyperplane. Let me draw it for you. So, and this will be your W vector. uh, okay, yes. So you can see these two are the decision boundaries, and this is the hyperplane. So x1 is a point on one decision boundary, x2 is the point on the another decision boundary, means x1 and x2 are the support vectors. And if we can see support vectors, the name suggests that these 2 points are not just point, it's a vector. That vector is computed from the origin. So in you will find that in only few books it has draw this diagram, that actually represent this point in form of a vector. Means it will start from the origin and end with that point. So this is vector x1, this is vector x2. So, and this is the W vector, which is nothing but projection of the W on the hyperplane. So this W vector is getting dot product with the this vector with x1 minus x2. So we have x1 vector, we have x2 vector, and this is the difference vector. So I hope you can visualize the thing now. So let us go back and try to calculate the value of D. So the width of the margin is the projection of this x1 minus x2 vector on the unit normal vector W. So if you can see unit normal vector of the hyperplane. So if you recall that W is something that on the hyperplane, it is on the hyperplane, and if you see unit normal vector, then it will be W divided by your magnitude of W. So, and if you are try to find a projection of x1 minus x2 on this hyper means this normal vector, then you just need to calculate a dot product of x1 minus x2 with the unit vector. And in that case, what you will get that this part from equation 3, it is 2. So we can compute the value of d that it is 2 by magnitude of w. So now we get a mathematical expression for d. So now we can maximize the value of d. So how we can maximize the value of 2 d? Just we can minimize the value of w. So we can maximize the value of d with this constraint also. We don't have to forget this constraint because there are two constraints on the two decision boundary, that w dot x plus b should be greater than 1 if the sample is from one positive side, that is 1, and if the dot product of w and x plus b is less than -1 if the sample is from the negative or the other class. So combine what you can do, instead of writing these two equations, you can just combine these two equations into one. Just multiply yi with this. So if you multiply yi by this, so what we will get, we will get this thing. A negative sign will change the direction and we will get this constraint. So what we have to do, we have to maximize the d with this constraint, and d is something that 2 by mod of w. So we can reverse the thing, in the sense that maximizing 2 by w is nothing, maximizing 2 by mod w is nothing but minimizing your w by 2. So this is very important point. And with the same constraint, with the same constraint, so there is two things to highlight here. One, that we have the objective function, that is a quadratic objective function, and the constraint are a linear constraint. So this type of means optimization problem comes under the umbrella of convex optimization. And the famous algorithm that people use to solve convex optimization problem is Lagrange multiplier method. So, oh, sorry, sir. So to solve any convex optimization problem, convex optimization in the sense that the objective function is in quadratic, and the constraint are linear. So that means scenario, that case of optimization comes into the case of convex optimization. And to solve this convex optimization, we have a standard method known as Lagrange multiplier method. So once you apply this Lagrange multiplier method over our case, our objective function and the constraint, so you can write these things into L equal to this equation. So where lambda i's are known as Lagrangian multipliers, and w and b are the model parameters. So there are two cases in Lagrange multiplier. One is equality constraint, one is inequality constraint. So the our optimization problem is of inequality constraint. So for inequality constraint, we have to follow one more constraint theorem, that is your Tucker constraint, that is your KKT constraint. So apart from applying your Lagrangian, means apart from getting this equation from the Lagrangian multiplier concept, you can you have to apply this constraint. First constraint is simple, that just differentiate your L that we have get from Lagrangian multiplier with respect to W with respect to B and put it equal to 0, then get the value. Uh, of equation 4, equation 5, all the Lagrangian multiplier are positive. The Lagrangian multiplier multiplied with the constraint should equal to 0 and the constraint itself. So solving this constraint are computationally very expensive. So what people do, people take the help of quadratic programming or numerical techniques to solve these types of equation. So and this form of your language multiplier equation is called primal form. Primal form, very important point to note that uh, this equation that I have represented in L, let me zoom it. Okay, wait. Yeah, this L people generally used to represent by L. Oh, sorry, LP, which is primal form. So there are two types of form associated with SVM while applying means solving that convex optimization through Lagrange multiplier approach. One is the primal form, another is the dual form. And dual form is very simple. So what you have to do, you have to just make use of this LP equation, and in that LP equation you have to put uh, this equation 4 and equation 5. So it's a simple derivation. What you have to do that the mod of w squared by 2 is something that 1 by 2 w into w transpose. So you just put this equation into LP, and when you solve, you will get the dual form that is represented by LD. So this is the dual form. So we will see why we are interested in dual form in the non-linear SVM case. So I just want to conclude the things here that for a linear case, first what we will do, we will solve all the set of equation that for LP we will solve LP with KKT constraint, all the equation we will solve and try to find a feasible solution. A feasible solution is that uh, which provide you the maximum hyperplane, means a possible solution, and then we can select that solution, that feasible solution which just give a maximum d. So once we get the maximum d, corresponding to that maximum d, we will try to get the value of w and b, because these are model parameters. And once we get w and b, then it is very simple to use it for classification purpose. We just need to use this equation that y is, we will say for a new data set, we have these two part, and we will get this part from the new data. Just compute this complete thing and see whether it is greater than 0, then it go to the positive class on the right side, and if it is negative, then it will go to the negative side. So uh, in a nutshell, what does a linear SVM do? It just find the maximum hyperplane, just get the maximum d value. Corresponding to that maximum d value, it gives you uh, w and b, that are model parameters. Once you get the w and b, then you can classify the things. But through the main typical part is to solve for a maximum d problem, because calculating maximum d comes under the convex optimization task. So this is the typical thing, but you don't need to worry, because there are several inbuilt functions are there. You don't need to solve these things on pen or paper. But life is not simple. So in real life we don't usually get the data set that get easily linearly separable. So I just want to let me zoom. I'm just struggling with this whiteboard. Yeah. So what we have discussed till now, we have discussed this case, a simple linearly separable data set. But what we have to do more practically is we have to deal with linearly not separable data set. So there are two concepts for the data set that are not linearly separable. So if I have given you a data that are not linearly separable, you can see in this diagram, you can there is no straight line possible to separate these two data set. So what you can say, that let me check whether the number of training point that violates the training linear separability concept is less. If it is less, then I will suggest you to go with linear SVM with soft margin. What does soft margin means, I will discuss within a few minutes. Just have a patience. And if the data set that violates the your linearly separable concept are high, means the data set that are not, means more non-linear. In that case, what we do, we just transform the data set from one space to another space, from one space to a higher dimension space, and try to figure out that in that space whether it is linear separable or not. So it is an interesting topic. So let me take this example only. Let me use the ruler. Let me go there. Let me rotate it a little bit. Yeah. Okay. Yeah. Let me try to draw a line that can separate. Yeah. So you can see. So for this particular case, what we can do, since there are only two data, there are only two data that violates the linearly separable principle. So we can use the soft margin concept to and we will apply that same linear SVM over this data, although it is not linearly separable, but only two outliers are there. So what does the soft margin means? So let me zoom into this part only. So it is used when the number of training data that violates the linear separability is less. Okay. So in this case, we modify the objective function. Yeah. So earlier we only have objective function with this part only. We have added a penalty part. Penalty in the sense there is no nothing free in this world. So you have to pay for everything. So what here we do, we will use a c as a multiplier, and we use the concept of the slack variable zeta. What zeta will do, it will put a relaxation on that margin. So instead of the equation, if you can see, earlier we have this part only. Earlier we have this part only for the equation of the decision boundary. We have that relaxed that the boundary with the variable called slack variable zeta I in both the cases, both the decision boundary. And we have multiplied the complete thing. We have multiplied the complete thing. Suppose there are two uh, data points that violates the linear separable principle. In that case, that two get summed up and get multiplied with c, and c is loss factor, and the higher the value of loss, we have to compensate that in the objective function, and the rest everything remain the same. So what you have to do, again you have to apply your Lagrange multiplier concept and the KKT constraint to get a optimal margin, and corresponding to that optimal margin, you have to get the W and B. Once you get the W and B, just use the simple equation that is I've already told you, that if that W dot X plus B is greater than 0, then it's come to the positive class, and in other case it comes to the other class. So this method we generally use when the number of variable that violates the linearly separable principle are very less, but that is not possible in the real scenario. So for the real scenario, what we usually do, we just transform the data. We just transform the data from one spatial domain to the other spatial domain using a transformation function. So if you can see, this is the dual form. So I have said that why we are interested in the dual form, because we are using this dual form equation for the nonlinear SVM, in the case of nonlinear SVM. And what we have to make only a few changes, that xi and xj is get mapped with the mapping function phi. So we have to just change xi with phi of xi. Phi is a function of xi, and xj with the function of phi xj. So that your dual form equation will get changed to this. We have just replaces xi and xj with the mapping function phi of xi and phi of xj, and that mapping function is nothing called nothing but the kernel. So when we get the term kernel, means people say which kernel you are using in support vector machine for classification, or support vector regression for regression problem. So there are some famous regression means sorry regression, I am telling that there are several famous kernel that you can find in this table with equation. So I will suggest you to go through this kernel, and there are one exponential kernel is also, that is also famous but is not mentioned here anyways. So uh, in this case where we have more number of data that violates the linear separability concept, so we just transform the data from one spatial domain to another higher dimension spatial domain using a mapping function, and just we change this mapping function with the kernel, and this is the value that we will substitute for. Suppose we are using linear kernel, then we will just put xt in that case, xi t with xj. So and we will use the mathematical formula here, and we'll compute the things if ld plus the kkt constraint to get a maximum d value, and through that maximum d correspondingly we get w and b. Once we get the w and b, we are done with the SVM classifier. So that's all that I was interested in to discuss with you in SVM topic. There are some other variant, means for regression purpose people have modified the support vector regression to means support vector machine for classification to support vector regression for regression problems. So since it avoid overfitting, so there are several paper that shows the potential of support vector regression in case of regression problem. So I will suggest you to go through that paper also, that have discussed means how we can use support vector machine for regression problem. And there will not be any hands-on video on SVM. I will share a link, means it's a very simple, that's why means I will share a link from a MATLAB blog. You can just go through that and try to apply SVM through MATLAB. So that's all for this lecture. Thank you so much. Let me close the recording.